We'll walk through solving this a few practice problems with the random variables very quickly. The sheet was given out in class a couple days ago, so we're going to draw a card from a standard deck of cards, right? There's 52 cards in a deck. Just those of you that aren't card aficionados. If we get a red card, we get nothing. A spade wins $5. For a club, we win 10, an additional 20 for the ace of clubs. So, how do we get $0? Well, that would be 26 out of the 52 cards, which would be 0.5. There's a 50% chance we walk away with nothing. How do we win $5? Well, we're going to have to get a spade. Well, there are 13 spades in a deck of cards. A fourth of the cards, or 25%, are there. Now, this one it might be a little bit easier to go to the very end. How many ways are there to get the $30? Well, there's one card. The one card out of the 52 would get us that money. So that's 0.019. And then for the other 12 spades, right? So basically these last two pieces of the chart, we're breaking up clubs, excuse me. You got the 12 clubs. Anything outside of the ace will get you the $10. The one card gets you the extra 20, which means for 30, you get a $30 payout for that particular card. So the 12 out of the 52 will be 0.231. Again, those should sum to 1, which they do in this particular case. So what's the probability we make some money? So in other words, what's the probability x is greater than 0? You could also write that. What's the probability x is greater than or equal to 5? That'd just be 0.25 plus 0.231 plus 0.019. So there's a 50% chance we make money. If we have to pay $5 to play, what's the probability we make money? Well, now all of a sudden, if you think about it, to make money, you have to make over that $5 amount that's right there. So now we want the probability that x is above 5, and that would just be 0.231 plus 0.019. In other words, you're pretty much going to have to get a club, whether it's just one of the regular clubs or the ace of clubs, and there's a 25% chance. So our probability dropped a little bit there. A couple plans to have children until they get a girl, but they agree they will not have more than 3 kids, even if they're all boys. So we're going to say 50-50 shot, boys and girls. So let's create a probability model for the number of children they might have. So first off, x, number of children. Consider what are the different how many kids could they end up having? Well, they could have 1, 2, or 3. So those are the values x could take on. So let's set up our probability model. So to have one child, well, they're going to go until they get a girl. So that would just be a girl. There's 0.5. 2 kids. That means they had to have a boy, and then they'd have a girl, which would be 0.5 times 0.5, which is 0.25. Right? Girl is not an option because once they had a girl, they would have stopped. Right? They can't do boy, boy because if they had boy, then a boy, they'd have another kid. They'd go for the girl. Or there's no guarantee they have a girl. So they could have boy, 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 boy. Well, the probability of boy and boy and boy is 0.125. Boy, boy, and boy, 0.125. That or means add, which means we end up with 0.25. So what's the probability they have 3 kids? Now that we got the table done, so what's the probability x equals 3? Go ahead and get used to writing those probability statements. We're going to be doing it a lot. 0.25. And what's the probability they have at least 1 kid? So greater than or equal to 1. Well, we're told they're going to have a child, so that probability is just 1. All right, another example, a carnival game offers a $100 cash prize if you break a balloon by throwing a dart. It's $5 to play, and you're willing to spend up to $20 to win. So that tells us we're willing to play up to 4 times. You estimate you have a 10% chance of hitting a balloon on any given throw, so we'll create a probability model. Now we're going to stop this game once we win. Otherwise, this table could get pretty out of hand pretty quickly. So the probability of a win is 0.1. And so we think, all right, so x, it'll be our net gain. So in other words, if you pay $5 and you win on your first throw, your net gain there would be $95. You got to account for how much you're willing to pay, right? If you have to pay $20 and you don't win until your 4th throw, you gain $80, right? So some of the values x could take on. If you win on your first throw, you walk away with $95. You're plus 95. If it takes 2 throws, 90. 3 throws, it would be $85. And if it takes you 4 throws to win, it's $80. The one a lot of people don't consider, well, you're not guaranteed to win at all. You could end up just throwing 4 balloons, losing them all, which means you walk away $20 less rich, $20 poorer. So this is the big one a lot of people kind of forget when they start to set up models like this. So here's our possible values. And I'm not doing number of throws here. The question asked me to create a probability model for your net gain. So that basically also kind of tells you what you should define your random variable to be. So read the question carefully, and it'll basically walk you into what you should. Let me get the right color here. What your x or your y, depending upon what your favorite random variable is. And I guess you could use really any variable, but x and y are probably the most popular. So, what's the probability that we win on the first throw? Well, that's just a win, which would be 0.1. If it takes you 2 throws to win, well, that would mean that you lost and then you won, right? And that'd be 0.1 times 0.9, which is 0.09. If it takes you 3 throws, that means you lost, you win. So that's 0.9, right? So the probability you lose is 0.9. So that'd be, this one right here would be 0.9 times 0.9 times 0.1, which would be 0.8081. And then if it takes you 4 throws, that'd be loss, and a loss, and a loss, and a win. So that's 0.9 times 0.9 times 0.9 times 0.9 times 0.1, which would be 0.0729. Notice I'm not really rounding here. I'm going to try to keep as many decimals around as possible. And then the probability that you walk away with nothing, in fact, that you walk away with less than nothing, right? You've lost $20. That'd be loss, 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 loss. So that's 0.9 to the 4th, and that's 0.6561. So the biggest probability you have is that you walk away with nothing. What's the probability your net gain is $90? So that's probability x equals 90. Again, once you have the chart set, it's pretty straightforward. You literally just go to the chart. What's the probability your net gain is at most 90? So x is less than or equal to 90 at most, which would be everything, kind of circle this part in the chart, everything from 90 and down. And you could add 0.09 plus 0.081 plus 0.729 plus 6. Or you could realize, well, this whole chart should add up to 1. You could just do 1 minus 0.1. So there's a 90% chance you walk away with at most $90. All right, one more example. So here's a situation where they're going to choose a random sample of 3 students to form some kind of advisory board. So they're just going to go out and randomly pick these students using appropriate methods. And 40% of students, so the probability that someone opposes is 0.4, which means the probability they support will be 0.6. So they're going to call 3 random students, A, B, and C. What's the probability that A and B support and C opposes? A and B and C. So in other words, we want the probability of support and oppose, which would be 0.6 times 0.6 times 0.4, which is 0.144. A 14% chance that we get that particular combination. So out of all the combinations of opinions that can be held, well, all 3 could oppose. You could have a support, A could support, and then B and C oppose. You could have a situation where A opposes, B supports, and C opposes. You have a situation where both A and B oppose, but C support. Maybe we have a situation where A and B support and C opposes. And what I'm really just doing is rearranging these. So that would be A and C support, B opposes. Or we could have support, oppose. Or we have one more situation, all 3 could support it. So really this is just a matter of, let's go through and calculate all the different probabilities. So right, oppose, this would be 0.4 times 0.4 times 0.4. All right, so 0.4 to the 3rd, 0.064. SOO, well this would be support is 0.6 times 0.4. Oop, I don't know what that's doing to me there. So this would be 0.6 times 0.4 times 0.4. That's 0.096. And for these two examples right there, it's the same letters, just in different combinations. So you're going to be multiplying the same numbers. We just saw in part A, here's S, two S's and one O would be 0.144. And then three straight supporters would be 0.6 to the third, should be 0.216. So let X be the random variable number of students who oppose. So X could take on the values, you could have 0 that oppose, 1 that oppose, 2 that oppose, or 3 that oppose. And so the probability of X in this scenario, right, we're using an advisory board of 3 people. That's why we're stopping at 3. And really what we've done in part B is we've come up with all the possible combinations. Now we're just going to put them into the table. So the probability that 0 people oppose it, well, that's this value right here that we're sitting on. So that's 0.216. The probability that all 3 oppose it, that's this number up here, 0.064. How many different ways can we have one person oppose it? So one person opposing, it's this one, or this one. So in other words, 0.144 plus 0.144 plus 0.144 would be 0.432. And then probability that 2 people oppose it, it'd be this one, or this one, or this one. So 0.096 times 3, 0.288. Now we can answer a question on a majority of the advisory board. So probability X is greater than or equal to 2, which would be 0.288 plus 0.064. So there's about a 35% chance that we get at least 2 out of 3 people on any randomly selected board that would oppose the funding.